Diode operation. A diode is a semiconductor component that allows current flow in only one direction. It can also be thought of as a one-way valve. It will allow current easily in one desired direction, but will block current from flowing in the opposite direction. The ability for current to flow through the diode depends on the voltage bias on the component. If the device is forward voltage biased, current will flow through the diode following the body diode's direction. Think of the triangle like an arrow. However, if the device is negatively voltage biased, current will not flow through the diode. The perpendicular line shows the body blocking direction. These basic diode operating principles are important for analyzing power converters, since diodes are very commonly used in many power electronic circuits. Here, we will learn about a very basic type of AC-DC converter that uses a single diode. As we saw, a diode is an electrical component that allows current to flow in one direction based on the voltage bias. If we have an AC source, like the wall power, and a DC load, we can use a diode to achieve a simple AC to DC converter. Let's take a closer look. Let's start with talking about a single diode AC-DC circuit. Here you can see a single diode used between an AC source and a DC load. Let's quickly review the operation of a diode. If the positive voltage and negative voltage is as shown, this is forward bias on the diode, then current will go through the diode as shown. If it's reverse bias, meaning this side is negative and the other side is positive, current will not flow through the system. So let's put this principle into action based on the input voltage and how it affects the output voltage. So first, in an AC input, we have the voltage on the positive side coming in here. This means that the positive and negative polarity is as shown. This means also that the voltage over the diode will be forward biased. So this means that current will flow from the input through the diode, through the resistor, like this. We have current flow in this direction. This means that the output will simply follow the input voltage like this. So here we can see when the input voltage is positive, our output voltage will essentially follow that same voltage. Next, let's look at the case for the negative voltage on the input. So here, our input is going to go negative, as shown here. This means that the voltage on this circuit diagram is going to be backwards. So the bottom will be positive and the top will be negative. This means that the voltage bias over this diode is also going to be backwards. This is reverse bias, which means current will not flow through our system. This means that the voltage will just be zero. So during this phase, our output voltage is simply 0. So when it's positive, we look at our full circuit here, you can see both diagrams. During the positive voltage cycle, current flows through the diode and the voltage is exactly the same. During the negative cycle, no current flows through the diode and our output voltage is simply 0. Next, let's look at a slight variation of this converter. We have our single diode as before, as shown here, and now we have a capacitor, and our capacitor is attached here. This is an output capacitor, and we use this capacitor to help smooth out the output voltage. So let's look at the operation of this system. It's going to be a little bit different. It'll come in 3 stages rather than 2. So let's start with the first stage. From the beginning, our input voltage is positive up to about this point. During this part, our input is positively biased, and we're going to have current flow through our diode, which is positively biased. And that current flow is going to go through our diode, and it's going to go into both the capacitor and the resistor to complete our circuit here. So on the output, our voltage will simply be the same as input voltage for this phase. So up to here, our output's going to be exactly the same. But at this point, something different is going to happen with our diode. So at this point in our input voltage, something happens. Our capacitor actually stores voltage. It stores the energy that we had before, and it's going to maintain that voltage. Once we hit this point, the voltage on the output, V out, is actually going to be higher than that of V in. So even though this is positive and negative, this voltage on the output is higher than that of the input. So what happens is this diode becomes negatively biased, and current will not flow through the diode. We'll only have current flowing through the capacitor. So the capacitor has some energy. It's going to put that energy into our output load, and the power will flow in this direction, as shown here. What this means about our output is that our voltage is actually going to decrease with the capacitor voltage. So up to this point, we will get our capacitance providing the energy, and it will decrease our voltage slowly. Once we hit this voltage, something else will happen. At this point, there's no more power in the capacitor. So we have no current flow, our diode is reverse biased, our capacitor has no more power in it, so no current flows anywhere. So what happens is our output voltage will simply be 0. And this is for this portion of it. Our input is going to be slightly negative. Once we hit this positive point again, we start our cycle completely over, and we get the first phase from the beginning one more time. So as we talked about in the very first part, we have positive voltage on the input, and current is flowing through our system to the capacitor and to the resistor, to our load. So here you can see our input waveform and our output waveform here. What we do for this capacitor, we added it in order to smooth out our output. So compared to the single diode without a capacitor, you can see our output here is a lot smoother. If we were to put a larger capacitor, we could actually get a even smoother output waveform. Maybe that would look like this. So here we've explained the waveforms for the input waveform from AC and how it smooths out the output using a diode and a capacitor AC-DC circuit. We covered one of the simplest AC to DC converters that uses just a single diode to change AC power into DC power. If a capacitor is added at the output voltage will be more steady. The advantage of this system is that it's very simple, but it also has some limitations. As we saw, this converter only draws power from the input when the input voltage is positive, and no power when the voltage is negative. This means that we are not fully utilizing the potential power draw from this basic converter. The single diode AC-DC rectifier can be used for low power and low cost applications as a simple converter implementation.